Hi everybody. Let's talk about our lesson for today, which is going to be the introduction to the periodic table. So you probably will want to take out your photocopy of the periodic table that I gave you, and we're going to fill in some information on that periodic table. Feel free to, if you want to, some kids use colored pencils and fill in different areas to shade in the regions of the different parts of the table or what have you, but that's not necessary. But if you'd like to do that, that's perfectly fine. So we are going to use the periodic table a lot in this class, and he'll become your new best friend, I guess you could say. You know a lot of this information already, that each box on the periodic table represents a different element. Here's our box, and this particular representation just has the element symbol. We all know what that top number is. That's the atomic number, and the bottom number is the average atomic mass, which we had a little lesson on how to calculate that as well. But different periodic tables will have different information within that box. You'll see the one on your on the table that I gave you is different than that box you see on the slideshow. So elements on the periodic table are arranged according to increasing atomic number. That hasn't always been the case, but it is the case on the current periodic table. And you'll notice a couple of places on the periodic table where the atomic number obviously goes up from left to right, but within the, if you look at the masses on the elements that do not necessarily correspond, that the mass gets larger as well. A couple of places where you'll notice that is if you look at cobalt and nickel. Cobalt has an atomic number of 27. Nickel has an atomic number of 28, but you'll notice that the mass, the average atomic mass of nickel is actually slightly smaller than the average atomic mass of cobalt. There are a couple other exceptions with that, tellurium and iodine, and there's a few other ones on the periodic table. But for the most part, as the atomic number increases, so does the average atomic mass, with a few exceptions. So Dmitri Mendeleev was one of the first people to put the periodic table in, or take the elements that were known at that time and organize them into a chart. There were other people that were doing this at the time, but he was the first one who really found the patterns that were existing among the elements known in his time, and he arranged them according to properties that he was seeing occurring. And there were holes in the chart because at that time there were many elements that had not been discovered, but he was able to accurately predict what certain properties would be of those elements that were not discovered yet, just based on the properties of the surrounding elements of where those holes were in the periodic table. It's kind of a neat thing. Now today's periodic table is arranged slightly different. If you take our periodic table and turn it 90 degrees, it would be more relevant to the way Mendeleev's table is laid out. Now what we do, we have some names that we use to describe the different regions of the periodic table. You may know a lot of these. If not, make sure that you understand these thoroughly. The elements are grouped into columns and rows. So our columns would be our vertical columns, and then the rows are horizontal. And they're grouped because of their similar chemical and physical properties. So our columns are called groups or families. So I want you to know both of those names, that the tall up and down columns, those are all called groups or families. And the elements that are found within that column or that family share similar chemical properties. So that means they behave similarly when they react with like elements. It doesn't mean they're exactly the same, but their properties are very similar. The columns are also numbered with a digit and a letter. Some periodic tables are numbered differently than others. The tall columns, which would be the first two columns and the last 6 columns, those would be numbered with a letter A. So it would be like 1A would be the first column, 2A would be the second column, etc. And those columns that are labeled with the letter A, those are called the representative elements, and that's a word that you're going to want to know. Whenever I say representative elements, you need to know which portion of the periodic table I'm talking about, and that would be the group A elements, those tall 8 columns, the first 2 at the beginning and then the last 6. Then there are some actual names that correspond to those groups. So group 1, the very first column on the periodic table is called group 1, and its name is called the alkali metals. So any of those metals within that first column are called alkali metals. Then the second column, group 2, right next to that, those are called alkali earth metals. So the thing that's different there is that word earth is snuggled in between the alkali word and the metal word. Sometimes this is called the alkaline earth, I-N-E at the end here. Don't worry about knowing that in terms of being able to regurgitate that to me, but if you do see it written as alkaline earth metals, know that that is proper. That is a proper way to call that. And then the last two columns that I want you to know their names of are the last two columns on the periodic table. Group 7 would be the second to last column on the periodic table. Those are called the halogens. And the very last column, group 8, are called the noble gases. An older name for that column was the inert elements or the inert gases, but the more common term for that are the noble gases. And again, some of you may already know those, but these 4 names, these would be like called family names: alkali metals, alkaline earth, halogens, and noble gases. Please, please, please know those. So if I in class say, well, the alkali earth metals, you need to know where I'm talking on the periodic table and which elements are included in that. So here's a periodic table that's found in your textbook. Part of it's cut off at the top here. I apologize for that. So what I would suggest is maybe on your periodic table, number these 1, 2, skip these short columns here, then go over here to the next tall column and label 3, 4, 5, 6, 7, 8 to the end. Another way to number these columns is not skipping these shorter columns and going straight from 1, 2, 3, 4, 5, 6, 7 and going to 18 at the end. I really prefer skipping numbering these shorter columns here for teaching purposes, really. The IUPAC, which is the International Organization for Chemistry, they have it numbered 1 through 18, but I really prefer 1, 2, skipping these here and going to 3 at the top of boron here and numbering that by just for teaching purposes. It makes it easier. So you might want to fill that in on your periodic table. Also, you'll notice you might want to label each of these columns, the 4 columns that I gave you names for. Now, notice in column 1 here, though, the alkali metals don't start until lithium. This element right here, hydrogen, is actually not a metal, even though he's on this side of the periodic table with the other metals. So please know that hydrogen is not an alkali metal. The first alkali metal in that column is lithium, and then the rest of them down below it. So you might want to fill that in on your periodic table. Then some other areas on the periodic table that I'd like you to know about are the transition metals. I'll go back real quick to this periodic table. The blue portion here, obviously you see them labeling that the transition metals. Those are the shorter columns. Please know that that area is the transition metals. Those are called the group B elements. So those are some other areas that you need to know. When you look at the periodic table, there are 3 types of elements. 3 types of elements. All the elements are classified into one or the other, one of those 3 groups. The first group we'll talk about are the metals. Most elements are metals. Let me go back to this periodic table again. So if you look at this table here, this zigzag line here, also called the stair-step line, that kind of divides 2 of our main types of elements. So all of the elements found to the left, lower left of this zigzag line are metals, and that includes these bottom 2 rows here as well. Now notice this black line here between hydrogen and lithium. That's separating hydrogen from these other metals, because hydrogen is not a metal. So that's where our metals are found. So you notice that most of the elements on the periodic table are metals. The next, and then there's some properties of metals, okay? So here are some properties of metals which you may have heard before. The first one is that they do conduct electricity. They have free-flowing valence electrons, which allow electric current to flow very readily. Some elements better than others. Number 2 is that they're malleable. Malleable means that's why people like to make jewelry out of metal, because it bends easily. They can pound it into different shapes and mold it to be what they like it to be. Then the other 2 are that it's ductile, which I think we mentioned before, but that means that you can take that metal and you can pull it and make it into a wire. Actually, it's more like pushing through a die, but we won't worry about that whole process. But that means that metals are able to be stretched, pulled to make a nice wire. Now, that doesn't mean it's stretchy like a rubber band. I mean, it takes a lot of force to do that, but you can change that diameter pretty easily with specific tools. And then the number 4 is another reason jewelry likes to be used for, or metal likes to be used for jewelry, and that's because it's lustrous. It's nice and shiny. And not all metals are. Sometimes they corrode really easily, so they're not always lustrous, but some of your noble metals are like gold and silver. Those are usually pretty shiny. So those are properties of the metallic elements. All right, and we talked about where they're found, so you can fill that in on your note packet. Then the next type of element, so we've talked about metals. The second type are nonmetals. Those are found, I'm going to go back here pretty quickly, right here. Those are found to the right side of the zigzag line. All of these elements over here are considered nonmetals. Now we'll talk about the ones that fall right on the zigzag line in a minute here. But these are all considered nonmetals. And what that means is they are not like metals. Okay, so we don't have a specific set of properties that can be used to describe all of the nonmetals because they're all kind of different from each other. Many of them are gases, a few are solids, one is a liquid. I guess one is a liquid, and there are a few solids. So these elements, as I said, are in the upper right-hand corner of the periodic table, and they lack the properties of metals. The third type of element on the periodic table are metalloids, also known as semi-metals, and they are found in between the metals on the periodic table and the nonmetals on the periodic table. So they fall right along the zigzag line, and they have mixtures of both metallic and non-metallic properties. So I'll go back to that periodic table in just a second, but they're found along the zigzag line and all of those elements except for aluminum. Aluminum is considered a pure metal even though it falls on that zigzag line, and please, please, please know that. That's an important element to know. So let me go back here to our periodic table. So when we talk about the zigzag line, we mean the boxes that actually form one part of that zigzag line, not just touching the corner. So boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Those would all be considered semi-metals except for aluminum. So that means that their properties of those elements are mixtures of metallic and non-metallic properties. Something to keep in mind is those elements that are on the right-hand side of the zigzag line here. We got boron, silicon, arsenic, tellurium, astatine. Those are all more like nonmetals because they lie on the side with the nonmetals. And then germanium, antimony, and polonium, those are more like metals. They have more metallic properties, thus they lie on the side closer to the metals. So something to keep in mind as well. All right, so then here's a more generic form of the periodic table with them divided. This particular periodic table does not have this as a blue box. I would like you to know this as a blue box, meaning that this element, which is boron, I would like you to classify that as a semi-metal, even though they don't have it that way on this periodic table. Okay, and these two white boxes here have not been updated, but they have been discovered. Okay, so this one here would be a semi-metal, and this one here would be a metal. Okay, so then in this next section, real quick here, I'd like you to look over the natural states of the elements, read through that section. There's some good information in there that I'd like you to know. A couple of things that we need to talk about from this section is that some elements are made up of molecules. So this means it's an element. The atoms are the same, but there's two atoms that are bonded together. And we saw this before in a couple of slides earlier. And these elements are called diatomic molecules or diatomic elements. That means it takes two atoms to make up that particular substance. That's how it's found in nature, is two of the same atoms that are bonded together. There are 7 of these elements that are found always as pairs when they're found in nature, and you do have to memorize them. Here they are. As they come up, you'll see they're all nonmetals. Okay, so we've got hydrogen. Notice we've got this little 2 here. That means that there are 2 atoms that are bonded together. We've got nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Now, you can either memorize them the way you see them here, okay, HNOFClBrI. Another way to memorize them is to go back to your periodic table. I'll show you real quick where they're found, and there's a little, kind of like a mnemonic device for this. But there are 7 diatomic elements. So if you find the 7 on the periodic table right here, nitrogen, and you make a 7, you go over 3 boxes and down 4. Okay, that's actually 6 of the 7, NOFClBrI. Okay, and then don't forget hydrogen over here. So those are the 7. So some people on their periodic table take a little colored pencil and color in those 6 boxes the same, and then color hydrogen's box that same color. That way they remember that those are the 7 elements that are diatomic. And this is crucial for remembering which ones these are throughout your entire chemistry career, however short or long it may be. For those of you, if this is your last year of chemistry, but those that are going on, either way, you need to make sure you remember those. There's another method for remembering the elements. Let me see if I can do this without messing up here real quick. Let me get the right color for you guys. I like the yellow. I hope it shows up. Maybe I better do red. Sorry, technical difficulties here. Let's do the orange. All right, so it's something called Hofbrinkel. H-O-F, Hofbrinkel, B-R-I-N-C-L. So those are the 7 diatomic elements in a mnemonic device, Hofbrinkel, and some people like to learn them that way instead of looking at the 7 on the periodic table and then this guy here. So you've got a couple different ways to try to remember those elements, and hopefully that will be helpful to you. Okay? All right, I'm going to erase all that ink. Oh, it didn't erase all of it. I wonder why. Interesting. Okay, so let's go back to where we were. So those are our 7 diatomic elements. Hofbrinkel is one way that you can remember those. The little red part still stayed on there, didn't it? See if I can get it to go away. Still isn't going. All right, well, whatever. Now here's a little picture that will give you a representation. I think we saw this earlier when I was talking about electrolysis with you. And that is saying that, let me switch this to the highlighter, the laser pointer, that'll be better. So we have 2 water molecules. When they are go through electrolysis, they split apart into their respective elements. And if you remember, we saw 2 atoms bonded. That makes an oxygen molecule. And we have a hydrogen molecule here and another hydrogen molecule here. And you'll notice that we have 4 hydrogen atoms here, and we also have 4 on this side. We have 2 oxygen atoms right here, and then we've got those same 2 oxygen atoms bonded here. And that's just the natural form of those 7 elements. When they're found in nature all by themselves, they actually pair up like that. It's kind of like co-joined twins, if you will. Okay, so another thing about this section is that some elements actually can be found in more than one type of crystal structure. And carbon's probably the most common element that you are aware of that does this. And these different crystal structures are called allotropes. And that's an easy word to confuse with isotopes. So please be careful with that, allotropes versus isotopes. So some different forms of carbon. Carbon can be found in the form of diamond. That's probably one of the most common form that you're familiar with. Another form, I guess, at least when you're in school, if you think of carbon in the form of graphite, which is found in your pencil, lead, which isn't really lead, it's got graphite in it. And then there's another form called buckyball, and that was fairly recently discovered. I think it was back in the 1980s sometime when this form of carbon was discovered. There's lots of other forms as well. There's something called nanotubes. Some of you may have heard of nanotubes. That's just a real thin layer of graphite that's wrapped in the form of a tube, and they're very, very stable. There's another form that's just been discovered recently called graphene. But anyway, the idea is that these are all made of carbon atoms, but the way those carbon atoms are bonded to each other gives them different crystal structures. Diamond is colorless. It's very, very hard. It reflects light beautifully. It's stable. And so it's a different form. And if you look at carbon and graphite, it's gray. It actually conducts electricity a little bit. It sheds off easily. That's why they use that for writing utensils, because as you press a little, those layers shed off and then marks are left on your paper. Buckyball, I'm not sure there's really a use for that, but the crystal structure for a buckyball would be like a soccer ball. The orientation of the atoms make such a shape that it looks like a soccer ball. They're all made of carbon atoms, but the way those carbon atoms bonded are different, and that's what makes those allotropes. Okay, so, and I think I'll leave the ions for another day. Maybe what you can do tonight for your homework then is a part of it is to fill in part of the ion section here, section 10. I'll give you more detail on Canvas in terms of how far I want you to go with filling in your note packet, if at all. So please make sure you check Canvas for your assignment for tonight. Thanks, you guys. See ya.